Hey everyone, Lily here. Welcome to week 3 of recorded mini lecture. So this week I have a very bad webcam, so I encourage you to please ignore that. But diving in this first portion, we'll be going over two graph traversal algorithms, BFS and DFS, so breadth first search and depth first search. As a quick reminder, every graph is a collection of vertices and some edges connecting them, but in the context of these algorithms, usually we treat vertices as objects with some sort of information that we want to access in a nice way. All right, so both DFS and BFS should be pretty familiar from CS61B, so we'll recall each of them briefly, but if that reminded you just how much you've forgotten in 61B, I highly encourage you to read the textbook on this more carefully. It'll have a lot of more in-depth explanation and examples that start sort of from the beginning. All right. So both BFS and DFS are graph traversal algorithms, and both of them work for both directed and undirected graphs. So in this first section, we will look at undirected graphs as examples, and we'll dive down a little bit deeper into directed graphs for depth first search in particular. All right, so let's start with BFS, breadth first search. So in this algorithm, we keep a queue of all the active vertices and also keep track of which vertices we've been to. So we start by putting in the starting vertex A into the queue. We mark it, and so at every iteration, we take out the first vertex in the queue, mark it as visited, and then put all of its children in. So let's see how this plays out. So the queue only has A right now, so we cross it off, we take it out of the queue, and we mark it as visited, do whatever we need to do, and then we put all of its children into the queue. So its children is B, C, D. So I'll put it in, B, C, D. You can do tiebreakers, you get to decide what you want to do with ties. But for the purpose of this, we'll just say it's B, C, and then D. All right? Then, so A is done. Then we go to the next element of the queue, we take out B, mark it as visited, and then put all of its children. Oh, but look, it doesn't have any children, so we're done. Done with B. So now we take C out of the queue, look at its children as E and D, but D is already in the queue, so we just put E, and then we mark C as visited. That's done. Now we take out D, mark it as visited. It doesn't have any children that that hasn't been visited already, so we are done. And at the very end, we take out E, mark it as visited, doesn't have any children, and the queue is empty, right? So then we're done with BFS. If you notice, essentially we're sort of traversing the graph by how far away vertices are from the vertex we started with. So we started with distance 0, we looked at A, and then we looked at all the ones that are distance 1 from the start of the initial vertex. So we did B, C, D. And then we did distance 2, which is E. So regardless of how big your graph is, you can make this as complicated as you want. But essentially, BFS will give you a traversal in the order of how far vertices are from the vertex you started with. So always you will be traversing the root vertex, and then all the ones with distance 1, distance 2, distance 3, so on. Okay. So that's BFS. Eventually, if we take sort of every time we go to the next vertex, if we mark the route we took there, so for example, we went from A to B, A to C, A to D, and then we went from C to E, then we have this tree, and this is called the BFS tree. The BFS tree usually will not contain all the edges in your graph, just because usually your graph isn't a tree, but that's what it is. It's a BFS tree marking which paths we took to each particular vertex. All right. So now let's do DFS. We saw that BFS is an iterative algorithm. We sort of iterate through a queue. For DFS, it's more recursive. It's a recursive algorithm, and it goes something like this. At each vertex, we start with vertex A again. At each vertex, we pre-visit the vertex, then recursively call DFS on each of its unvisited children, and then post-visit it. So let's unpack that. So we always pre-visit on some vertex B, and then call DFS on its children, and then we post-visit. and then return. Okay, so let's see how this plays out. We start with DFS, calling DFS on the vertex A, and then we pre-visit A, so we mark the timestamp as 1 for the pre-visit, and then we call DFS on each of its children. So the first one we call is B, so we call DFS on B. Okay, so let's go to B. What happens when DFS is called on B? We pre-visit B, so we get timestamp 2, and then we call DFS on each of its children. There are no children for B, so we're done. Now we post-visit B, 3, right? And then we return, so B returns. Now remember how we were in this step of calling DFS on each of A's children, so now we go to the next children of A, which is C. So we call DFS on C. So then we pre-visit C, 4, and then we call DFS on each of its children. So that would be, the first one would be E, right? So we call DFS on E. So we pre-visit E, and then we post-visit because E doesn't have any children, so we skip this step. Now we post-visit and return. E returns, so now we go back to C. C has another child, so it's D, so we call DFS on D. So we pre-visit D, 7, right, because we're just at 6. And then we look at if the children of D, see if they have been looked at before. But see that we've already pre-visited both children of D, so we don't visit them all over again. We just have to return from D, or post-visit D, and then return from D. So D is done, and we go back to C, and we see that both of C's children have already been visited. So C is also done, we can post-visit C. Okay, once we've post-visited C, we return from C, and we go back to A. Now look at A. All of A's children have already been completely visited, so we just post-visit A after, since we were at the children's stage, and the timestamp is 10, and we return. So if we sort of trace out how this, what paths we took, we can trace out that we went to B from A, and then we went to C from A, and then we went to E and D from C, and then we went back to A. Right? So this, we can see that this is a drastically different graph than this guy, right? The tree is different, but this is just because for here, whenever we have a child, we go as deep as we want. We go as deep as we possibly could before returning, right? We literally finish doing all of his children before we return, so we visit as many descendants of each node as we possibly could. Okay, so this is returned from DFS and is coupled with a set of tuples for all of our vertices. Its pre-visit number and its post-visit number, we call them pre and post. And then we'll see how these will become very useful for us in the coming section. In the DFS algorithm, we don't travel along every edge. This is perhaps not so surprising to you because there are a lot of paths to a particular vertex, and we only wind up needing one to get to it. So what are all the other edges? There are actually 4 kinds of edges characterized by their relation to, say, this entire DFS algorithm. So let's look at them. There are 4 kinds of edges, as I said. So there's forward edge, back edge, tree edge, and cross edge. So what are they? A forward edge is from a node to its non-child descendant. So an edge from A to D would be a forward edge. Now backward edge is going backwards. So it's from some descendant to its ancestor. This is a back edge. A tree edge is something that's existing in the DFS tree, so it's pointing from some node to its child. So this is a tree edge. And a cross edge is something that's none of the above. So this would be a cross edge. There are some interesting things we can say about how to classify them. Like, how do you tell if I just give you, if I don't give you the graph, but just give you the pre and post numbers of a DFS algorithm, how do you know what sort of edge it is? So let's think. For a forward edge or a tree edge, we're pointing, say U to V, we're pointing from some parent to some descendant, right? So then from this sort of algorithm, we know that we will pre-visit the parent first before visiting the descendant by definition, but then the descendant has to return and post-visit before the parent does. So what this means is that if we draw on a timeline, we first pre-visit U, the parent, and then we pre-visit V, and then we post-visit V, which is the child, and at the very end, we post-visit the parent. So it's like, if this is your V, then it's completely contained in this thing U. This is U from here. All right, so this holds for both forward and tree edges. And you can imagine for backward edges, it's the opposite way, that when you're pointing U to V from a descendant to a parent, then the parent would have been pre-visited first and post-visited last. So the graph looks something like this. The descendant, U, will again lie within the sort of the confines or constraints of its parent, V. So this would be, pre-visit V, pre-visit U. Oh, I'm doing a bad job of discerning the U and V here. Forgive me. Post U, and then at last post V. So from these two, it's very clear that if you're a child, you're going to be sort of enveloped by your ancestor or your parent. Now, cross edge is a little bit different. You can probably see that cross edges have sort of nothing to do with each other. It's like pointing to something that's already been visited completely, or pointing to something that just, have nothing to do with you. So perhaps it's worth saying that if you have a cross edge from U to V, then you're just disjoint. You'll have, pre-visit of U, and then pre-visit of V. Oh wait, actually you pre-visit V first, because you always point to something that you've already visited. If you're pointing to something you haven't visited, then you should visit that one first, because it's an unvisited child. All right, so I made a mistake here, forgive me. It has to go the other way. All right. Yeah, this would make more sense, right? Because once you're visiting C, it doesn't have any children because the arrow is pointing the wrong way. So then when you're visiting D, you'll see this sort of child C, but it's already been visited. So then we get this nice condition where V has already been visited before U even happened. So this would be pre and post of U. All right, cool. So essentially, by how the pre and post numbers are ordered, we can classify whether it's a forward edge, backward edge, or a cross edge. All right, and these are like timelines. Cool. All right, so that's it for the sort of edges classification. There's one more property that I want to discuss, which is how to tell if a graph is connected. So it turns out that a graph is connected if and only if its DFS is a tree rather than a forest. So think about it like this. DFS has only one tree, no forest, if and only if your graph is connected. Okay. So basically what this says is that if you can visit everything in one passive DFS, then everything is reachable, so G is connected. On the other hand, if G is connected, then every node can be visited via some other node. So then once we run DFS on it, it'll only have one tree rather than a forest because you never have to start anew. All right. Cool. And that's it for the first section of this mini lecture, and then Neil will take it over with strongly connected components. Thank you.
Hey everyone, in this video we're going to be covering a really fundamental graph algorithm called the SCC algorithm, where SCC stands for strongly connected components. Let's start with some really important definitions that we need to know. And so the first one here is the DAG, where DAG stands for directed acyclic graphs. And a DAG is essentially a directed graph that doesn't have any cycles, right? Which essentially means, as Lily covered in the previous video, it's a graph that doesn't have any back edges. And so the graph drawn here, A, B, C, D, E, you can see that there's no back edges, there's no cycles, which also means there's no back edges, right? All of the edges kind of move, quote unquote, like forward to the right, right? And so that's essentially what a DAG is. Now, the second definition is connectedness in directed graphs. So in an undirected setting, it's pretty straightforward to think about, right? If you have a node A and a node B, and there's an edge between them, that means those two nodes are connected. But in a directed setting, let's say you have node A and node B, and there's an edge from node A to node B, right? So for example, if you have something like this, if there's an edge from node A to node B, you can get from A to B, but you can't get from B to A. And that's kind of what makes the notion of, that's kind of why we have to change our notion of what connectedness is. So in order to say in a directed context that node A and B are connected, we're gonna have to be able to go from A to B as well as B to A. And then we can say A and B are connected in a directed setting. Now, this doesn't mean there has to be an edge from A to B and an edge from B to A. You can also have something like A to, I don't know, some other node D to B, and B just kind of points back to A. In this example, you can get from A to B through D, and you can also get from B to A directly. And so since you can get from A to B and B to A, you can say that A and B are connected in a directed setting. And so that's kind of a concept that we build on when we talk about the strongly connected components algorithm. And so essentially what a strongly connected component is if you have a directed graph, if you can get from any one node in that graph to any other node in that directed graph, then we say that graph is strongly connected. So these are some really important definitions to understand. They're also all in chapter 3 of the textbook. Really recommend reading that chapter. But anyway, moving forward onto kind of the core, kind of like an overview of the SCC algorithm. So essentially, so let's look at this graph, for example. Ignore the dotted lines for now. We'll get to that later. But let's say you have nodes A, B, C, et cetera, all the way to L, right? There's a bunch of nodes, and it's a directed setting. So there's a bunch of directed edges too. What we want to find here, so our goal is to essentially find a DAG of strongly connected components. What do I mean by that? What I mean by that is, so if you look at A is connected to itself, obviously. So that's kind of like a strongly connected component in of itself. If you see B and E, right, B and E, you see that you can get from B to E through this edge, and E to B through this edge. That kind of means you can go from B to E back and forth, which also means that they form a strongly connected component, right? And so essentially what we're trying to do is we're trying to find all of these strongly connected components here. Now, if you look at node C, right, you can't go from there's no way from node C back over to node A. There's no path in this graph that allows that. And so that's why node C and node A are in two different strongly connected components. Essentially, our goal is to find all of the strongly connected components. And what I mean by this term DAG of strongly connected components is that if you look at this graph here, right? You can kind of take now, like, let's consider the dotted lines. The dotted lines, essentially, it's kind of the answer. It represents all of the strongly connected components in this graph. And so you can have A as one strongly connected component, B comma E as another strongly connected component. And you see this edge, A connects to B. So we can say that A strongly connected component connects to this strongly connected component. We also have D as one strongly connected component. So we have that. We also have CF as another strongly connected component. So we can draw something like that. And we also have GIJ, HKL, all of those like nodes form a strongly connected component as well. I'm just gonna write ... because I'm lazy. But that kind of forms a strongly connected component too, connected from, and there's an edge from BE, connected component, and CF. And so again, just to overview that again, you have a strongly connected component A. There's an edge. This edge is what I drew here. So that's kind of that. So A, the strongly connected component A connects to BE. BE connects to CF. CF connects to GHIJKL, right? And so if you look at this huge kind of graph, it should kind of ring a bell. It essentially looks like a directed acyclic graph, right? There's no cycles in it. If you view each of these big blobs as a node, it's basically a big DAG of those nodes, right? And so each of these nodes are essentially strongly connected components. So our goal in the strong SCC algorithm is to find this DAG of strongly connected components. In the next video, we're going to cover the actual algorithm to do that. Two important definitions to understand are the concept of a sink node and source in a graph, in a directed graph. So if you can see here, it should be a little bit intuitive, but essentially a sink is one with no outgoing edges. So if you see from E, there's no edges starting from E and going anywhere else. And the source is kind of like this quote unquote starting node. More formally, what that means is if you run DFS on this graph, the source node is the one that's going to have the highest post order, right? But in more like common terms, it's kind of the one that starts, quote unquote starts. It's like the leftmost, or like it kind of comes before all of the other nodes. And so using those two definitions, before going into the actual algorithm, we're going to have to talk about two lemmas, or two really important facts. The first one is, so let's get into the first one actually. So in this kind of like a directed graph, you can see that this kind of dotted line with GHIJKL, that's going to be the sink, right? And this A is going to be the source. Again, this kind of follows from this diagram here. As you can see, if you treat this as a DAG, you're going to see that A is kind of like the leftmost. It's like the one that's starting the whole thing off. That's going to be the source. And G through L, like that strongly connected component, it's kind of like the bottommost. It's the one with no outgoing edges, so that's going to be the sink strongly. It's going to be the sink strongly connected component. And so another kind of thing, sorry, to go back, is when we're talking about this algorithm, it's really helpful to view entire strongly connected components as individual nodes, right? So we have this whole GHIJKL. We're treating that collection of nodes, that collection, that strongly connected component, as one node in our directed acyclic graph, this one. But yeah, anyway, so the first lemma relates to this. If we start with a node in the sink SCC, which is, if we start with any of GHIJKL, let's start with, I don't know, let's start with J. Why not? if we run explore, like the explore function, which essentially means if we start from J and we explore all of its neighbors recursively, right? What we're gonna end up with is exactly the sync SCC. And so what do I mean by that? What I mean by that is, so let's kind of like work through this explore process. So if we start with J, I is a neighbor, right? I'm gonna mark nodes by crossing them out, right? So we start with J, sorry. So we start with J, let's cross that out. We go to I is a neighbor, let's cross that out. We can go from I to G, let's cross that out. We go from G to H, let's cross that out. Let's go from H to K, we can cross that out. K to L, let's cross that out, et cetera, right? We're pretty much done there. And so if you see, if we start like recursively going through a node J, we've covered all of the nodes in the sync strongly connected component, right? So that is lemma 1. Let me just write that down to be extra clear. So recursively exploring a node in the sync SCC will yield, So essentially recursively exploring a node in the sync SCC will yield exactly the sync SCC. So it's a really important kind of like concept to understand. We're going to be using that fact for our algorithm. Yeah. So what is the second lemma? Essentially, we need two lemmas for this algorithm. The second lemma is saying, okay, let's say we have one strongly connected component C and another strongly connected component C prime. So in C, I have A, B, C, D. As you can verify for yourselves, it's strongly connected. You can go from any node to any other node. And in C prime, you have E, F, G. Again, it's a strongly connected component. Now, if we have an edge from a node in C to a node in C prime, and so that's what I mean by this dotted edge. There's an edge from B to E. So again, if we have an edge from a node in C to a node in C prime, if we call DFS on this entire graph, we can kind of view this like A, B, C, D, E, F, G as one big graph. If we call DFS on it, the node with the highest post order is going to lie in C. So let's kind of walk through that, right? Let's say we start our DFS process from node A. You're going to go from like A to B to C to D. And then you're going to backtrack to B. You're going to go from B to E to F to G. And then you're going to go back. So essentially what that means is, again, a reminder is you call like the pre-order is when you start a node, and a post order is when you're done with the node, right? So you start into node A, it's going to have the lowest like pre-order. You start from node A, you go from A, B, C, D, you explore E, F, G, and then you go all the way back to A, which means A is going to have the highest post order. Let's say, just for like argument's sake, let's say we start our DFS process from E. You go from E to F to G, and you're done with that side of things. So E's post order is going to be like 3 or whatever. So you're done exploring C prime, but again, you have A, B, C, D. So you're going to start DFS from one of these nodes. Let's say A, you go from A to B to C to D, back to C to B to A. So A is going to have the highest post order. Yeah. So essentially what that concept is saying is that anytime we call DFS on some structure like this, C and C prime, where there's an edge from C to C prime, the element with the highest post order is always going to lie in node C. So again, these are the two lemmas. The first one is if you explore a node in a sync SCC, you're going to get exactly that sync SCC. And the second is if you have C and C prime and an edge from C to C prime, C will have the one with the highest post order. And so given those two lemmas, we can kind of develop our algorithm from there, right? So what can we kind of do knowing this information? So the first lemma, it kind of tells us like, all right, we have this kind of basic way of finding a strongly connected component if we can start from the sink, right? Because we just start from a sink, we kind of like explore, like recursively explore, we get the entire sink strongly connected component. So we can have that. We can essentially kind of like, we can ignore that sink strongly connected component, go to the next sink strongly connected component, explore that, and kind of repeat that process. But the trouble here is, how do you even go about finding a sink node, right? How can you find a node in the sink strongly connected component? Because lemma 1 is only helpful to us if we know, if we have a sink node that we can start with, right? For example, in our previous example, we started with J, right? But we're going to have to identify one of these nodes as existing in the sink strongly connected component. How do we do that? So for that, we use lemma 2 as well. And then we kind of go into this, sorry, before going there, C is going to have this, so in this lemma, C is going to have the highest post number. So if you view C and C prime as this is one strongly connected component, this is another strongly connected component, there's an edge, this will be the source, this will be the source SCC. And so we have a lemma that says, all right, it kind of helps identify the source. We have a lemma that says, if we have the sink SCC, we can get that SCC. So we have to combine these two lemmas to help us out. So in order to do that, what we do is, the first step of our algorithm is to reverse G. So it'll kind of be, it'll make sense. It'll make more sense as to like how that's going to help us out. So again, we go from G here, we flip all of the edges, and we go to GR. That kind of denotes like the reverse G. So as you can tell, like all of the edges are essentially reversed. And so what is that going to help us do essentially? So now we have this, as you can see, like all the edges face the opposite directions. So now this is going to be the source SCC. And now this is going to be the sink SCC. Essentially the roles are reversed, right? In the reverse graph. And so this lemma helps us identify the source strongly connected component. What do we have to do in order to do that? All we have to do is, in this reversed graph, we run DFS. What DFS is going to return is, it's going to return a bunch of post order numbers. You take the element with the highest post order. What this lemma told us is the source SCC will have that highest post number. So if we run DFS on GR, we're going to get the node with the highest post order, and that highest post order will exist in the source strongly connected component, which is this, right? But that should kind of ring a bell. This SCC was exactly the sink SCC in the normal graph, in the graph we started with. So now what do we do? So we've identified essentially a node. We've identified, let's just say for argument's sake, I was the one with the highest post order in DFS, right? So we've identified a node in the source SCC in the reverse graph, which means we have a node in the sink SCC in the real graph that we care about. And so now we can use the first lemma, which means recursively exploring a node in the sink SCC will yield exactly that SCC. So now that we know that I must exist in the sink SCC in the regular graph, we can go back to the regular graph, run kind of this recursive explore function on I, and that's going to give us exactly this sink strongly connected component. What can we do then? We can just kind of like check mark all these nodes, kind of like disregard them, and repeat the process. The next highest post order must the next highest post order in GR must be either C or F, for example, right? Because now C and F form the source SCC in G reverse. And as we see here, let's say C was the one with the next highest post order. We call like explore on that. It gives us this. We disregard these. We kind of check mark those off. All right, that's another SCC. We go to the next one and we kind of recursively go through that process. We check mark D, we check mark BE, and we check mark A. And so that's essentially how the algorithm works. So the first step was to reverse G. The next step was to, starting with the node with the highest post order in G, we run the undirected connected component algorithm. What that means is it's just like fancy language for saying the recursive explore function. We kind of run that, starting with the node with the highest post order, and that'll give us one SCC. We kind of, we're done with that SCC. We go on to the next one with the highest post order, and we continue that process until we're done processing the entire graph. And that's going to give us all of these strongly connected components. And so that's kind of like the general algorithm. One takeaway that I really like to emphasize in this algorithm is, yeah, it's like I just threw a ton of information at you, but a really important tip to use, maybe you should take inspiration from this algorithm, is that a lot of times when you might be stuck on a problem, it can be really helpful to modify the graph in some way. And so for this example, how we modified the graph was reversing all of the edges. That might come in handy for you. Another example of modifying the graph might be adding an edge. Adding some node that could like help you out. So a lot of times modifying the fundamental graph itself can give you ideas for how to develop an algorithm for a problem. But yeah, that's pretty much it as to the SCC algorithm.